that could learn to cluster similar inputs into a two-dimensional map, representing different speech sounds, for example, by different processing units in the map, with similar inputs activating neighboring regions of the output space. A major advantage of the Kohonen network model was that it did not require a category label for each input. Generating labels to train supervised networks is expensive. Kohonen had only one arrow in his quiver, but it was a very fine arrow. In a promising early attempt to systematize probabilistic networks, Judea Pearl at the University of California, Los Angeles, UCLA, introduced belief networks that linked the items in the network with probabilities, such as the probabilities that the grass is wet because the sprinkler came on, or because it rained. Although Pearl's network model was a powerful framework for keeping track of cause and effect in the world, manually assigning all of the required probabilities proved impractical. A breakthrough was needed for automatically finding the probabilities with learning algorithms, as will be discussed in Part 2. These and other network-based models all had one fatal flaw in common. None of them worked well enough to solve problems in the real world. Moreover, the pioneers who developed them rarely collaborated with one another, making it even more difficult to make progress. As a consequence, very few in the leading AI research centers at MIT, Stanford, and Carnegie Mellon took neural networks seriously. Rule-based symbol processing received most of the funding and generated most of the jobs. Early Pioneers. In 1979, Geoffrey Hinton and James Anderson, a psychologist at Brown University, organized the Parallel Models of Associative Memory workshop in La Jolla, California. Most participants were meeting one another for the first time. As a postdoctoral fellow of neurobiology at Harvard Medical School who had written only a few highly technical papers on neural networks published in obscure journals, I was surprised to be invited to the workshop. Geoffrey later told me that he had vetted me with David Marr, a towering figure in neural network modeling and a leading visionary at the MIT AI lab. I first met Marr in a small workshop in Jackson Hole, Wyoming in 1976. We had similar interests, and he invited me to visit him and give a talk at MIT. Marr received a bachelor's degree in mathematics and his doctorate in physiology from Cambridge University. His doctoral advisor was Giles Brindley, a physiologist who specialized on the retina and color vision, but also was known for his work on musicology and the treatment of erectile dysfunction. He famously dropped his pants during a lecture at a meeting of the American Urological Association in Las Vegas, Nevada, to demonstrate the effectiveness of a chemically induced erection. Marr's doctoral dissertation described a neural network model of learning in the cerebellum, a part of the brain that is involved with fast motor control. He also developed neural network models of the hippocampus and the cerebral cortex, described in dense papers that have proven to be prescient. When I first met Marr at Jackson Hole, he had already moved to MIT, where he was working on vision, and where, as a charismatic figure, he had attracted talented students to work with him. Pursuing a bottom-up strategy, he started at the retina, where light is converted to electrical signals, and asked how signals in the retina encoded the features of objects and how the visual cortex represented the surfaces and boundaries of objects. He and Tommaso Poggio developed an ingenious recurrent neural network model for stereo vision with feedback connections to detect the depth of an object from the slight lateral displacements of the images of dots in the two eyes in random dot stereograms. Binocular depth perception is the basis for how magic eye images pop out at you. 2 years after Marr died of leukemia in 1980 at the age of 35, the book he was working on at the time, Vision, was published posthumously. Ironically, despite the bottom-up approach Marr took to his research on vision, starting with the retina and modeling each succeeding stage of visual processing, his book is best known for advocating a top-down strategy, starting with a computational analysis of the problem to be solved, followed by building an algorithm to solve the problem, and finally by implementing the algorithm in hardware. But even though this may be a good way to explain things after you have figured them out, it isn't such a good way to discover what's going on in the brain.